recording and the presentation out on Building America's website. I'll provide a link at the end. If you have a question, everyone right now, all attendees are in a listen-only mode, so you are muted, and you can submit your questions through the question pane on your screen. We will answer questions at the end of the presentation and try to answer as many as we can as time permits. We also offer AIA and ICC continuing education credit. If you are an AIA member, I will provide a link at the end of this webinar, and you'll want to take down that link and go to that URL and submit your name and your AIA number, and we will submit them to AIA for your credit. If you want ICC continuing education credit, we're also going to offer that certificate of attendance. It'll have the ICC course number on there, and you'll need to submit it to ICC yourself, so you'll do self-reporting. Or if you're with a professional organization, ASHRAE chapter, or whatever it might be, use that certificate of attendance. And again, you'll want to take down that URL and get a request for a certificate. Those will go out within a week. And if you have any questions, then of course you can reach me via or send an email through the registration email that you received when you got your confirmation for attending today. All right, so the course today, little course description. I'm not going to read all that because Joe's going to get into all the details. But basically what we're going to cover is the new provisions that are going to take place in the 2018 IRC, not so much the IECC, but it does affect the IECC, and the additional benefits about these provisions for unvented attics, and all the research that Joe has done through Building Science Corp to get there, and what it took to get these code provisions in the code, and then some resources and tools available to help you not just with this provision, but other things that might come your way in doing your building design or for code officials, plan review, and inspections. So next one. So our learning objectives for today's webinar is, well, we hope that you take away, and again, submit questions as we go through this presentation, is understanding how the moisture can be controlled in unvented attics, and then proper ways for roof ventilation measures for unvented attics, and also how to apply these new measures. Joe will be talking about some vapor diffusion ports and how those can be installed. So we're hoping that what you'll take away today is understanding these best practices and then the resources to go to get the additional information. So if this is something that you do in your field, or you're a designer, or you're a roof contractor, that you have this information available. And so what I like to do is introduce Joe Lstiburek. He's been an engineer for a long time, over 35 years, so many degrees. I couldn't even, PhD, mechanical engineering, you name it, all from the university. So I like tag teaming with Joe. We've done this only a few times, but it's really nice to be able to present with Joe. He's an awesome speaker. And so I'm going to let Joe take over. He is the owner of Building Science Corporation, and go ahead, Joe. It's all yours.
Well, thank you very much, Pam. Let's talk about what the specific code change was. Unvented conditioned attics have been allowed on the prescriptive side of the code since the early 2000s, but we had a code change that has put a twist to what can and cannot be constructed. In climate zones 1, 2, and 3, basically the hot climates, both hot, dry, and hot, humid, instead of having to go and use half-pound density or 2-pound density spray polyurethane foam on the underside of the roof deck, or having to put rigid insulation on the top of the roof deck, we're able to use netted cellulose or netted fiberglass or blown adhered cellulose or blown adhered fiberglass on the underside of the roof deck with no soffit venting, no air space between the insulation and the roof deck, but a ridge vent. But the ridge vent has a twist to it. The normal gap in the ridge vent that allows air to leak out is covered with something very vapor open. with a high permeance. Think of a high temperature Tyvek or Typar or Lstiburek. And so the idea is that we're allowing that opening to be vapor open but airtight. And on the top of that space, or on top of that membrane or layer, goes a traditional roof vent. So you still have a roof vent, but you're not venting air. Air is not carrying moisture out of an assembly. The moisture is leaving the assembly by the process of vapor diffusion, hence the term vapor diffusion port. Those of you that have ever been involved in the code making process, I wanted to call it a vapor diffusion vent, but oh my God, that'll be too confusing. So it's a vapor diffusion port. The area is 1 to 600 of the ceiling area, and the reason that that number was picked was, one, it works. It actually provides more area, diffusion area, than you actually need, but the typical area of a traditionally made on the market off-the-shelf ridge vent is actually 1 to 600, whereas the code currently calls for 1 to 300 ventilation area, split 50-50 high-low. Well, 1/2 of 1 to 300 is 1 to 600, so the logic was you're able to use standard off-the-shelf ridge vents. You just apply an airtight vapor open layer under them. The vapor permeance of that layer has to be greater than 20 perms. This, however, does not work for flat roofs. It has to have a sloped roof, and the reason for that is that moisture-laden air is less dense and more buoyant, and so the moisture-laden air ends up at the peak. But if there's no peak, if there's no slope, this technology doesn't work. So we need a vent area of 1 to 600, a permeance of that vent area being greater than 20 perms. The slope has to be greater than 312. Now, there's more. There needs to be active air change between the attic area and the house or the occupied space. We're truly conditioning this. We're having a means of controlling the moisture in that space, and that's done by basically providing supply air. The amount of air that's supplied is 50 CFM per 100 square feet of ceiling area. This number comes from our work, believe it or not, with leaky duct work. When ducts were installed in a leaky way, you're typically in an attic, you're typically getting this amount of air, and that provided sufficient moisture removal until we learned how to make ductwork tight. So the irony is we make our ductwork tight and then we add 50 CFM. The reason that we chose 50 CFM, even though you only need about 40-ish through the work that we've done, is 50 CFM is also the amount of air that we introduce when we have conditioned crawl spaces. So we chose the vent areas to make it consistent with other language and other equipment options and material options, and to not have things that confused. So 50 CFM of supply air for an attic, 50 CFM of supply air to a crawl space, 1 to 600 is the vent area. No new materials have to be invented to make this work. The code language currently calls for insulation to be installed directly under the roof deck. We'll see later in the discussion that that's really not strictly necessary, but that's where the code language happens to be at in this particular iteration. And again, this only works in climate zones 1, 2, and 3 from the code perspective. We're currently doing work in climate zones 4, 5, 6, and 7, and I expect this technology to be extended there in the next round, but with certain additional restrictions. So we're not ready for prime time in climate zones 4, 5, 6, and 7, but we're warming up. We're off Broadway. We're playing the Poconos before we're ready to go to Broadway, but we will be playing Broadway next round. This is the code definition of a vapor diffusion port. Basically, it's a means of allowing the moisture to pass through in the vapor form from the attic to the atmosphere. So let's now talk about the physics, the past experience, what we can and cannot do with vented and unvented attics in all of the climate zones, and then towards the end we'll focus on the narrow provisions, the narrowness of the provisions of the current code language, and why, and where we're likely to end up in a couple of years. Nothing excites an engineer of my age than starting off presentations with the Arrhenius equation. I mean, there's just this, there's nothing, it's right up there with Newton's laws of motion and Einstein's relativity. Then you got Arrhenius, and there are jokes that we can't tell, but Savant Arrhenius basically came up with the third most famous equation in physics, won the Nobel Prize in the turn of the last century. Was a huge scandal because he was a chemist. Nothing irritates physicists more than having to give a Nobel Prize in physics to a chemist. But what Arrhenius basically said that the more energy involved on a material, the worse problems can be. And so he never doesn't explain it this way. The physics says activation energy. What that means is that the hotter a roof is, the shorter its life. The more exposed to ultraviolet light, the shorter its life. The more exposed to humidity, the shorter its life. 10 degrees Kelvin is about 20 degrees Fahrenheit, and as the temperature of roof membrane increases 20 degrees, its useful service life is reduced by 50%. This is sort of an exponential thing. And so the hotter things are, the more energy is available. Sometimes bad things happen, sometimes good things happen. When we went from black roofs to white roofs, the white roofing membranes lasted longer, but the roofs got colder, which meant that their ability to dry was reduced because drying is a function of energy. So when we went to light-colored membranes, light-colored shingles, green, basically cool roof technology, the moisture, dwell time for moisture in the systems went up. Similarly, we went from low levels of thermal resistance in the attics to high levels of thermal resistance. The more and more insulation, the lower and lower the drying potential. The lower and lower the drying potential, the greater the risk for moisture damage, such as decay, corrosion, condensation, mold, biological nasties, and so on. So there's no such thing as a free thermodynamic lunch. We saved a great deal of energy, we increased the life of the membrane, but we decreased the life of the stuff underneath because we didn't have energy available to evaporate things. That has required the entire re-examination of how roofing assemblies actually work when they are extremely energy efficient. The three principal damage functions that the Arrhenius equation covers are basically water, heat, and ultraviolet light, and all of them play a role in the performance of roofs. Basically, where a building touches the sky, the damage functions exert or apply the most amount of damage. It's not easy to get a good high-performance, long-lived roofing system in place, and we have Arrhenius to blame for it. We need to chat a little bit about vapor pressure and relative humidity, and forgive me for this. I know many of you are extremely knowledgeable about these things, but I want to go over them because sometimes, even though we're familiar with them, the implications of some of these things we sometimes miss, and it's those implications that become pretty significant to us. If I have a cube that's hollow, made out of glass, it's 1 cubic foot in volume, that is signified by this red box here on this image. It contains 1 cubic foot of air. And let's assume that in that 1 cubic foot, of glass that's hollow, I have 1 trillion molecules of water in the vapor form. So my water vapor density is 1 trillion molecules per cubic foot. We don't use that language because we don't want normal people to understand that. We invented a term called vapor pressure. What the heck is that? Well, vapor pressure really means water vapor density. So the water vapor density, or the vapor pressure, and the upper pair of cubes at the top of this image are 1 trillion molecules per cubic foot. Now, it turns out that if that space is at 75 degrees Fahrenheit, if that cubic foot of volume is at 75 degrees Fahrenheit, we can fit almost 2 trillion molecules in the vapor form in that space. If we tried to put in 3, 1 trillion would turn into condensation and condense on the side of the cube, and 2 trillion would be in the vapor form. So it's got 1 trillion in it, but it could hold up to 2 trillion. It's 50% of the way to capacity, halfway to capacity. Its relative humidity is 50%. So relative humidity is the amount of moisture in a space compared to the total amount of moisture that space can hold at that particular temperature. So there you go. So if I take that glass cube at 75 degrees Fahrenheit and just cool it to 60 degrees Fahrenheit, I reduce the ability of the space to hold moisture by 50%. So I haven't changed the vapor pressure. The water vapor density in that cube is the same, but by merely cooling it from 75 to 60, I've reduced the capacity of that space to 1 trillion molecules. There was 1 trillion in it, so the relative humidity is 100%. This is kind of scary and weird and everything else in that we can change relative humidity not by changing the water vapor density or vapor pressure. We can do it just by changing temperature. So I haven't added any water or taken any water away in that upper example. I've just changed the temperature. In the lower pair of examples, I've got the same cube to start with, 2 trillion molecules in a space, 1 trillion molecules in a space that can hold 2 trillion at a temperature of 75 degrees Fahrenheit. Of course, it's 50% relative humidity. Well, now I'm going to pull a fast one. Instead of changing the temperature, I'm going to add 1 trillion molecules. So I'm going to increase the water vapor density to 1.5 trillion molecules per cubic foot. I'm going to increase the vapor pressure. And of course, now the relative humidity is increased to 75%. So I can change relative humidity 2 ways. I can do it by changing the temperature or by changing the vapor pressure. Now here's the tricky part. Hygroscopic materials don't care how you do it. They just care what the relative humidity is. So wood materials, for example, engineered wood materials, see relative humidity. They don't see vapor pressure. Another way of explaining this is that the amount of moisture that can be held in a space in the vapor form is signified by the size of the cup. So I've got a really big cup on one end. So the 90 degree Fahrenheit cup is the largest there, and it's half filled with water molecules. So its relative humidity is 50%. Well, the cup beside it, the 75 degree Fahrenheit cup, is half the size. Every 15 degree drop in temperature, I reduce the capacity of a space to hold moisture by 50%. So it's half filled. So it's, of course, got a relative humidity of 50%. The next cup over is 60 degrees Fahrenheit. It's 1/4 of the size of the 90 degree Fahrenheit cup. It's at 50% relative humidity. The cup beside that is at 45 degrees Fahrenheit. It's 1/8 the size, half filled, 50% relative humidity. And then we got the smallest cup, half filled. It's 1/16 of the size of the 90 degree Fahrenheit cup. They're all filled with halfway, so they all have the same relative humidity, but it's pretty darn clear that they don't have the same vapor pressure. Hygroscopic materials like wood don't care. I can have very little moisture in outside air in the wintertime, but that moisture that's held is very close to the capacity that air can hold at that temperature, so the relative humidity is high. It's not unusual during cold weather to have an 80 or 90% relative humidity and say that, well, there's not very much moisture in that air. The vapor pressure is low, but the relative humidity is high. When it goes above 100% and it's below 32 degrees Fahrenheit, we call that snow. Anyway, you get the idea here. What's weird and important for us to appreciate and understand is that hygroscopic materials don't care how big the cup is. They only care how filled it is. From a heating perspective, if I take cold outside air at 35 degrees Fahrenheit and 90 degrees relative humidity, and I warm it to 70 degrees Fahrenheit, I dump that air into a larger cup and I drop its relative humidity. So if I take cold outside air at a high relative humidity, but at a low vapor pressure, and I heat it, I dramatically drop its relative humidity. If I'm dealing with air conditioning, I take hot, humid air from the outside, 90 degrees Fahrenheit, 90% relative humidity, and I run it through an air conditioning system. The air conditioning coils are typically at 55 degrees Fahrenheit. That's a pretty darn small cup. I dump the big cup into the small cup and it overflows. That overflowing is called condensation, and that's the condensate that drains out of the air conditioning system. Well, the air coming off of that air conditioning cooling coil is miserable air, 100% relative humidity, 55 degrees Fahrenheit. The only thing that likes that would be a French wine bottle and a French crawl space. Most of us don't live in French crawl spaces or French wine bottles, so we need to change that. We take that air and we dump it into a 75 degree Fahrenheit cup. We add energy to it. When we add energy to it, the relative humidity drops. The problem is that if I don't have the energy to add, if I don't have heat gain from the sun or heat loss from the building or someplace, that relative humidity stays high and bad things can happen. All of this is explained on the psychrometric chart, and we're not going to get into it, but it's basically the size of the cups that matter. Absorption isotherms are basically what we use to describe how much moisture is picked up by a hygroscopic material. We have this funky little curve that basically says that as the relative humidity goes up, the moisture content goes up for these types of materials. A non-hygroscopic material doesn't have a curvy shape. It's a straight line and it's horizontal. Wood materials are hygroscopic. They see relative humidity, and the way that we describe that is we basically describe it in terms of the physics by saying it follows the sorption isotherm for a hygroscopic material. These are the sorption isotherms for the materials that we typically build with. All of the interesting stuff that we build with is hygroscopic, and all of them are weird because all of them see relative humidity and they don't care much about the vapor pressure. Mother Nature had a wicked, evil sense of humor. The sorption isotherms are temperature sensitive only in a small degree, and so an engineer will hate it when a physicist will hate it when an engineer says temperature doesn't matter. Well, it matters a little bit, but not enough for an engineer to care about it, but apparently enough for a physicist to passionately care about it. That's why physicists and engineers can't communicate. We're dysfunctional. We only focus as engineers on the important stuff. The physicist gets lost in the physics, and what can I tell you? So to take into account the temperature variability, we make the curve fuzzy. So we have an error bar. What's important here is that this is a curve for wood. It basically says that when wood, let's just plywood or spruce or pine, even OSB, which is basically a softwood composite and engineered wood, sees a relative humidity of around 25%. it's at a moisture content of about 6%. When it sees 60%, it's somewhere around 12%. So in the wintertime, it's not unusual to have 20-25% relative humidity inside your building. In the summertime, it's not unusual to have it around 60%. So the moisture content varies between 6 and 12%. This is a big deal for people who are installing wood floors and wood trim. I mean, you want to install these materials at the midpoint at 9% moisture content by weight, so that the movement only ranges from 9 to 12 or from 9 to 6, because if it goes from 6 to 12, your floors will buckle, or if it goes from 12 to 6, you're going to get big gaps in your floor. All right, on to the second law of thermodynamics. I promise we're going to be done with this real soon. The impacts of the second law simply mean that heat flow is from warm to cold. Why? Because of the second law. Moisture flows from warm to cold. Why? Because. Moisture flows from more to less. Because. Air flows from a higher pressure to lower pressure. Because. Gravity acts down. Because. All right, well, that has implications to us if we look at a map of North America. Where we are impacts what direction things are moving. What time of season we're at impacts what direction things are moving. So roof systems, attic systems, wall systems, foundation systems don't work the same way in Miami and in Montreal, or in Minneapolis and Memphis and Monterey and the Mojave. Where you are matters, as does the amount of rainfall. Obviously, the roofing technologies to be used in Biloxi, Mississippi that gets 4 inches of rain an hour are different than the roofing systems that we need to deal with in Las Vegas, Nevada, which gets 4 inches of rain a year. So the amount of rain matters with roofing systems as well as everything else, and temperature and humidity vary and impact how these systems work as well. So we need to know where we are so we know what the external environmental loads are going to be. Here's an aha moment. Vented attics, therefore, are climate dependent. So the air you're venting with in Vancouver, Canada, is different than the air you're venting with in Miami, Florida. And both of those are very different than the air you're venting an attic with in Columbus, Ohio. This is a classic traditional vented roof, vented attic technology or approach. It works well in all climates, but it works differently in those climates. So we have a similar means of construction, but how the system works varies from one part of North America to another part of North America. Venting an attic with hot, humid air brings moisture in. Venting an attic with cold, humid air brings moisture in. I actually got that right, so let me give it to you again. Venting an attic with hot, humid air brings moisture in. Venting an attic with cold, humid air brings moisture in. In the wintertime, the air outside in Vancouver is cold, but very humid. So when you vent an attic in Vancouver, you're not removing moisture, you're bringing it in. Hold that thought. When I'm venting a roof in Miami with hot, humid air, when I vent it, I'm bringing moisture in. Well, how the heck does this possibly work? Well, we need a little bit of physics, vapor pressure, relative humidity, and whatever. So soffits typically bring air in, and ridge and off-ridge vents, the upper vents, let air out. Not too many people appreciate this graph. I certainly didn't for many, many years. Vapor pressure, the absolute amount of moisture, the water vapor density in air, doesn't change very quickly. It's pretty much flat between day and night. So in other words, the water vapor density over a 24-hour, 36-hour, 48-hour period is fairly flat, and that's the red line. But I know you're going to be shocked at this. Most people are. At night, it's colder than during the day. Well, if the vapor pressure is the same, as the temperature drops, the relative humidity goes up. So at night, the relative humidity goes up because it's colder. During the day, the relative humidity goes down because it's warmer. So this sinusoid basically shows the change in relative humidity on a daily or diurnal cycle. If I'm ventilating my attic at night, I'm bringing moisture in. If I'm ventilating my attic during the day, I often tend to remove moisture. So at night, the ventilation is charging the hygroscopic materials, and during the day, the venting removes the moisture. If there's energy available to get the moisture out of the hygroscopic materials. So you have to think of your attic as a moisture capacitor that is charged typically at night with high relative humidity air and then discharges during the day if it's sunny, because the sun elevates the temperatures of the roof deck and drives the moisture out. So you're charging it at night, you're discharging it mid-morning. Mid-morning, these vented attics tend to feel like a steam bath because you're basically driving the moisture out. This is carried out with air change. Well, when the air temperature goes to 120, 130 degrees Fahrenheit, by the mid-afternoon, it's very, very dry. We're actually creating a solar kiln in the attic. So we're kiln drying the roof during the day in the late afternoon, but we're charging it at night. What's been working for us is that the amount of drying has been dramatically greater than the amount of wetting in most parts of North America. But that balance has changed with green roof technology and high levels of thermal resistance. We no longer have the energy available to evaporate the water. So let's say I build a super insulated R2000 house in Canada or a super insulated passive house in Seattle. I've got no energy from the house, and it's cloudy in Seattle most of the winter, and the same thing in Vancouver. That's why they're all coffee addicts and they have that crazy grunge music stuff, because they're all depressed. So when we ventilate those highly insulated attics in Seattle and Vancouver, we charge the hygroscopic materials, but we don't have the energy available to discharge. So once we get above R60 insulation in a cold climate, we're actually getting mold now in these places. Now, that doesn't happen in Edmonton because Edmonton gets some sun. It's actually colder, but I get enough energy to knock the moisture out of those roof assemblies so that I have a bit of a drying potential. So believe it or not, I have mold problems in highly insulated attics in Seattle and Vancouver, but I don't have them in Saskatoon and in Edmonton and in Salt Lake City. I go to Miami, I get mold because I've now gone to tile roofs, which means that the roofs get colder, and I have radiant barriers, which means that the roofs and everything get colder. I have ductwork in those attics. When I bring in hot, humid air at night, during the day, the stuff doesn't get hot enough to evaporate things, and I'm now building up moisture. The ducts sweat a lot more. If I had poorly insulated attics, if I didn't have tile roofs, I didn't have radiant barriers, I wouldn't be seeing all of this. So when we were building energy inefficient buildings, we got away with a lot. A high performance building, we don't have that flexibility anymore. So when we add mechanical systems to this, things get really wonky. And again, almost all of you listening to this, I know that when we have leaky ductwork, we end up with high air change. The house tends to go to a negative pressure. We increase the latent load in the house because we're inducing infiltration, but that escaping air into the attic help semi-condition it. I mean, the house sucked, but the attic not so much. course, now that we have tight ductwork, the house doesn't suck. We don't have conditioning happening in the attic either. We've saved a lot of energy, but now things are wetter in the attic than they ever were. The best way of doing things, of course, is to put everything inside. Nobody ever has argued about this. It's just not easy to do. So we went to the technology of moving the insulation from the flat ceiling to the slope. We did that because it was more practical to get high levels of airtightness than to try to move the ductwork and have an airtight ceiling. This works better than this. Let me repeat. This works better than this, but this is typically easier to construct. This is about 10 to 15% more energy efficient than this, but this is 30 to 40% more energy inefficient than everything else. So this is horrible. This is a huge improvement. This is just a big improvement. So big improvement, huge improvement, difficult to build, easy to build. More expensive, but easier to build. Can we make our ductwork perfectly airtight? Yes, in a dream. All we can do is get better than we have. It's insanely complicated to get below 3 to 5% leakage on your duct distribution system. The fact that we're that low is remarkable, but you're not ever going to go below that. Back in the day, we were 10 to 25% leaky. So this is a huge improvement, but ducts still leak. And when you put them in an attic and the duct board and the duct insulation is R8 and the rest of the attic is R38, you're kind of wondering, am I still losing the game because the ducts are losing so much energy or gaining so much energy, depending on whether we're talking heating or cooling? We need to get better, and so this is where we're going with this presentation. So, we tried the soffits and the drops, and I'm here to tell you that it's not easy. It has aesthetic implications, and it's expensive. So it's not easy. The aesthetics are complicated, and it's expensive. So naturally, the industry completely picked up on it. That's an ironic statement. I hope that I can sense there's laughter and smiles through the internet. I have that internet sensor happening here. When we go to a conditioned attic, we increase the volume. People say, oh my God, it's an energy penalty. But when we go to the conditioned attic, even though we increase the volume and the surface area is greater, the air change has significantly been reduced. I typically reduce the infiltration by 50% from a standard vented attic assembly with leaky ductwork to a conditioned attic, even though the surface area is greater. That, of course, has had tremendous implication on how we size things. We have to fool the computer sizing systems to give us the right answer, because they're programmed to do infiltration based on volume. And so even though I have a conditioned space with a larger volume and larger surface area, my air change is dramatically reduced, but the computer calculation gives me the wrong answer. So we've learned to set the infiltration number to 0 and then put an arbitrary number in based on experience. So we're guessing at the right answer because we know what the right answer is because we've been doing this a long time. So if we were to, and what's the harm in oversizing? Well, then if the air conditioning system doesn't run long enough, it doesn't dehumidify, and we're going to see a little bit that it's all about the humidity. The original unvented conditioned roof technology derived from flat roofs, where we're just basically taking a highly successful technology in commercial roofing systems and sloping them, where we'd have our air control layer on the top of the deck, rigid insulation, another nailing surface, and shingles. This works like a champ. There's no issues with this approach in any climate zone. with the proviso that when we get into an area with a lot of snow, we end up having to have a vented over roof over the top of the unvented under roof to handle the thermal resistance of the snow to control ice damming. So when the ground snow load goes above 50 pounds a square foot, you need a vented over roof over the top of an unvented under roof, or you're going to get ice dams. This is a map of the United States showing the snow load area. Wherever the numbers are above 50, you have to have roof venting to control ice damming. Just trust me, this is a big deal. You can't stop ice damming with just an R60 or R80 roof, because the thermal resistance of the snow is gonna whack you. Let's now talk about my favorite thing to talk about ever, of course, is dew point. Dew point calculations are pretty much a waste of time because the dew point temperature might be in the middle of a wall, but the dew point location is always on the back side of the sheathing. So when somebody asks, where's the dew point, you don't have to do a calculation, so it's on the back side of the sheathing. So when condensation occurs, you have a change in phase, and that change in phase energy has to be dissipated. So you need two things for condensation. You need a surface below the dew point temperature, and you have to have that surface having sufficient thermal mass to handle the change in phase. We call that a condensing surface, and the first condensing surface you see in a wall assembly is the backside of the sheathing. Another way of saying this is that the temperature of the backside of the sheathing controls everything that happens in the wall. If you control the temperature of that surface, you get to control everything that happens in the wall. And this is just an example where even though the dew point temperature is reached partially in the middle of this insulation, all of the moisture and frost accumulate on the backside of the sheathing because the cavity insulation doesn't have sufficient thermal mass to handle the change in phase energy. Why do we care about that? Well, if we know where the stuff is going to end up, we can deal with it once it gets there, or we can change the characteristics of those surfaces because we know that the stuff is going to want to get there. If we change those characteristics, we can be in control. One of the ways that this is explained as in a classic building science text or physics textbook, Straub and Burnett is one of the better ones. So actually I think the best, not one of the better ones, the best. But it's written in Canadian. It has U and vapor, so that might confuse some people. The first condensing surface in old buildings was typically the inside pane of glass, and the colder that surface, the more condensation. We controlled condensation on glass by going to double glazing and triple glazing. We're basically warming up the temperature of the glass. Well, as we warmed up the temperature of the inside pane of glass, we moved the condensing surface in these houses from the windows to the wall cavities themselves. So we moved them from the window to the backside of the sheathing. Well, when that sheathing was vapor open and allowed moisture to pass through, the only damage we ever got was peeling paint on our cladding systems. Well, now with OSB and engineered wood, the moisture doesn't pass through. We now have a serious problem in those wall cavities. We found through practice and experience that installing an air barrier and a vapor barrier on the inside are not up to the task to limit the problems. So bottom line, we need double glazing and triple glazing over the exterior sheathing. That, of course, is what we call continuous insulation. This is the plot of the outside temperature over a one-year period in my hometown of Toronto, and there's really no thermal resistance associated with the OSB or plywood sheathing, so that exterior temperature curve is a pretty good approximation of what the temperature of the condensing surface in the wall is. Now, if we kept the humidity below, the relative humidity below 20% during December and January, I would never have to worry about condensation in my wall in Toronto. This is a curve for Toronto. If I increase the relative humidity to 35%, that shaded area shows me how much moisture is accumulating, and I have a problem. But if I warm up the temperature of the condensing surface with continuous insulation, I dramatically reduce the moisture accumulation, so I can increase the level of humidity inside of my building and not have a risk for condensation. So that's how we learned how to control condensation in wall systems, by controlling the temperature of the condensing surface. If I now slope that at 45 degrees and call it a cathedral ceiling, you understand the physics behind unvented conditioned ceilings, conditioned roofs that are allowed to be constructed in the code because we place sufficient thermal rigid insulation on the top of the roof deck to control the level of condensation. The amount of insulation we have to add on the top of the deck to do this depends on two things: where we are located from a climate perspective. Obviously, Minneapolis needs more rigid insulation than Memphis, and the amount of moisture that we have inside of the building. An indoor swimming pool or an art gallery constructed in Minnesota has a different internal load than basically a house. So you're going to need a lot more rigid insulation on the outside of your roofing system in Minnesota with an art gallery than you will with a house. This is not new technology. This was figured out in the 1950s, but apparently people didn't like to read books written in the 1950s in black and white. We have computer programs that can do it now in color. This was one calculation for the entire year. This is the sum of 8,800 calculations, one for every hour of the year. They more or less end up giving you the same answer. One of the things that we learned back in the day was that the condensing surface in a vented attic, or in an attic in general, tended to be the underside of the roof deck. So even though the dew point temperature was found in the middle of the insulation, the moisture would accumulate or change phase on the underside of the roof deck. So the roof deck temperature had a big impact, and that roof deck temperature was impacted by the color of the roof and whether or not the place was cloudy or not. If we have a cloudless night, that roof sees outer space, and the roof deck temperature through radiation exchange with the roof deck and almost at absolute zero will cause the roof deck to drop on the order of 8 to 10 degrees below the ambient temperature. That's why we get frost on roofs, even though it never drops below freezing in many locations. It basically tells us that all the moisture goes to the cold spot. The coldest spot are the nails, followed by the sheathing. The rafters or the truss members are typically unaffected. So the typical tell that you have damage happening in your building is when the shingles blow off, because the nail holding capacity of your sheathing is affected. You don't typically get a collapse, but you do get the shingles to blow off. One of the ways of reducing this was to take that wall with continuous insulation and put it on the slope, and we're now controlling the temperature of the condensing surface with rigid insulation. We don't have to flush the moisture out with attic ventilation. So this is the first technology applied to constructing unvented roofs, with having a mixture of insulation under the roof deck and on the top of the roof deck. The current language of the IRC and the IBC specifies what those ratios are depending on where you are. So climate zone 3 has a different ratio than climate zone 5. The higher the climate zone, the colder the climate, the greater the proportion of insulation you need on the top of the deck compared to the cavity to control condensation. In some parts of the country where we have a tile roof, the tile is on battens, we can have a vapor permeable roofing material, and that allows the roof deck to dry into that airspace. So in places like Las Vegas and Phoenix and hot, dry climates, the code says if you have a tile roof and you have a vapor permeable roofing felt, you don't need rigid insulation to control the temperature of the condensing surface. Moisture will still condense, but it'll be wicked through the material and evaporate on the other side by diffusion and into that airspace and go to the outside. Could this work in a hot, humid climate? The code doesn't allow it in a hot, humid climate. Well, why? Well, not humid climates. The roofing papers are not papers. They're basically impregnated asphalt or fully adhered membranes, and they are vapor barriers. So this only works if that roofing membrane is vapor open. It doesn't work if it's vapor closed. Asphalt shingles are vapor closed, so we don't allow this in the code with an asphalt shingle roof in places like Las Vegas or Phoenix, but we only allow it with tile in Vegas or Phoenix because we're assuming that the roofing material under the tile is vapor open. When I first did this work in 1995 and got the code language to be changed, no fully adhered roofing membranes that were vapor permeable were available. Today, we do have vapor permeable fully adhered roofing membranes available to us, so this could work in Miami if the roofing paper was replaced with a fully adhered vapor permeable membrane. Understand that that's not allowed prescriptively in the code, but it does work from a performance perspective, and it would be accepted under an engineered seal or an architect's seal. That's a code change that will likely occur in the future. The first technologies that took over the market were, of course, netted cellulose with tile roofs, and there are several 100,000 roofs in the last 20 years constructed in Las Vegas and Phoenix this way. We had some fun with unvented roofs accidentally in Phoenix, where we just had a flat roof, membrane that's impermeable, filled it, no ventilation, and seemingly the roofs actually worked. Well, they worked because the membranes were black. That membrane went to 180 degrees, 190 degrees, so the moisture from the inside might migrate up during the 1 month of winter that you have in Phoenix. It would be driven back down during the day because of the high temperature. When we changed the membrane color from black to white, we ended up with roofing problems in Phoenix simply because we changed the color of the membrane, and that changed the ratio of the wetting to the drying over the season. The thing that was noticed first was truss uplift, where the upper members would get colder or hotter depending on the color or the amount of insulation. And if the upper cord of a truss gets colder, it has a higher relative humidity equilibrium, so it picks up moisture and it expands. The lower cord is under the insulation. It's warmer. Its relative humidity is lower, so it contracts. Upper cord expands, lower cord contracts, and the truss bows upwards, and we have cracking in the ceiling. We began to see this in Phoenix with flat roofs because the upper cord got cold because it was white under a white membrane. So we had interior cracking of gypsum board, and that was the tell that told us to look inside and say, oh my gosh, we're actually getting moisture accumulating on the underside of this OSB sheathing under this white membrane, even though we never got it with a black membrane. If you attach the interior walls to the bottom cord of the truss, it lifts off the floor. These are enormous forces. The solution in cold climates, of course, with truss uplift was to have floating corners, so when the truss bows up, the drywall bends. This was the first negative implication of adding insulation to attics that are vented in cold climates. So we had low levels of attic insulation in a cold climate, say R30. Heat from the house warmed up the attic. So the attic temperature is roughly halfway between the outside temperature and the inside temperature. Because the attic was warmer than the outside, the relative humidity that the upper cord of the trusses saw was not particularly very high. But when we went to R50 insulation, R60 insulation, the bottom cord didn't get any warmer, but the top cord got incredibly cold, and we made it colder even still by venting it, or having a high ventilation ratio of 1 to 300. That caused the upper cord to swell. So truss uplift was increased when we increased thermal resistance in cold climates and ventilated the attics according to the 1 to 300 ratio. The solution was to let the attic truss move and let the drywall float free, hence floating corners. And so this is the technology of the day. This still works. We don't have the truss movement, but you now go to Vancouver and Seattle, high levels of thermal insulation in those attics. We now have mold for similar reasons because we've changed the temperature condition in the attic. Therefore, we've changed the relative humidity condition in the attic. Therefore, with the sorption curves, we've changed the moisture content. We learned that we had to basically balloon frame our interior cathedral ceiling assemblies. Say in a master bedroom, we couldn't have a truss as an end. We had to stick frame it, because if we had a truss, the truss would cause that wall to lift. By framing it with non-truss assembly, it didn't move. Therefore, we didn't get the crack. In Phoenix, the solution was to add rigid insulation on the top, so that the temperature difference between the top of the top cord and the bottom cord was reduced. This was a great retrofit. In new construction, folks began to use low density and high density spray insulation on the underside to reduce this movement when we went to a white membrane. Well, if it works for Phoenix and the flat roof, we found that we had hybrid approaches that we could use in colder climates. Again, the ratio of the spray to the fluffy stuff depended on where we were located. We just simply took the tables in the code that provided ratios between the insulation on the top and in the cavity, and simply said that the ratio would apply to the foam itself, not to the insulation on the top of the deck. That's where those numbers came from. Nothing prevented us from having the entire insulation assembly done with basically spray foam, and this technology took off first in South Florida and then migrated north. Low density foams were able to be used up to climate zone number 4. High density foam is the only stuff that's viable for climate zones 5 and more, because the low density foam is 2 vapor open. So high density works in all climate zones. Low density works only from climate zones 1 to 4. And folks know about this. Code allowed for almost 2 decades. This is a map of the United States, basically with the climate zones. It gives you an indication of what climate zones, open cell versus closed cell, work, and where the ratio of insulation is how it's specified in the codes. We were concerned in the early days, would we have moisture driven down through the top? And the answer is sometimes yes. We didn't know what the magnitude was. We could figure out the direction from first principles, but not the magnitude. So we constructed test structures in various climates, various permeances with various combinations of insulation to be able to say, is this an issue or not an issue? And the short answer is, inward drive is not an issue. Too little of it happens for us to worry about. But we didn't know until we knew. That's why we did the experiments. One of the things that we learned was that the attics had to be conditioned, not unvented. The conditioning happened accidentally when we had leaky ductwork. When we made the ductwork tight, we didn't have any moisture removal mechanism, hence we're now beginning to see some high humidities in unvented attics that are not conditioned, where we have a hygroscopic material with sufficient storage capacity to basically act as that capacitor. That only happens with low density spray foam and OSB or plywood. The capacitor is the OSB or plywood, and the moisture gets to the capacitor through the vapor openness of the low density foam. A high density foam, the moisture doesn't get to the moisture capacitor, so it's not an issue. The easy solution is to provide air change in the attic. How much? 50 CFM per 1,000 square feet. Did this cause a durability issue with the roof sheathing? The answer is yes. If you have a black membrane roof in Phoenix or in Las Vegas over OSB, that OSB is going to go to 180 degrees and it's beyond its service limit, and it will become embrittled, and it will lose its strength over time. So thou shalt not install black membranes over OSB in places like Phoenix or in Las Vegas. White membranes dramatically reduce the temperature of that and increase the life of our sheathings. Was there much of an effect on shingle temperature? No, believe it or not, the temperature of the shingles didn't change very much, but the temperature of the sheathing did. So we didn't have much of an impact on shingle life, but we had more of an impact on the life of the sheathing, but only in hot climates. What about places like Florida? Well, what saves us in Florida is that we have a lot of white membranes, we have a lot of tile roofs, we have a lot of cool roof technology. The life of the plywood and the OSB is not affected. The actual life of the materials are not affected. Arrhenius equation. Bad news is roof decks don't get as hot anymore, so I don't have as much energy available to evaporate moisture from the underside, hence the requirement for air change. Do I hate radiant barriers? No, I don't hate radiant barriers, but their implications, they work. Everything inside is going to get colder, therefore things are going to sweat more because everything is colder. So here's a good technology. Why don't we have basically a vapor open roof assembly and allow the moisture through? Well, that of course doesn't work with the radiant barrier because the radiant barrier, even when it's perforated, doesn't allow as much moisture to leave. But if I know that the moisture is less dense and more buoyant than dry air and it ends up at the ridge, I could end up with a vapor diffusion vent at the ridge, allowing the moisture out and not having a problem. Well, could we apply this approach to shingles, maybe having a drainage mat, something like cedar breather under asphalt shingles? We played with this and it didn't work. It works for a tile roof, but we couldn't get enough moisture removal through a 3/8 inch or a 1/4 inch or a 1/2 inch or 3/4 inch drainage mat. And once we got to higher thicknesses, there was no way we could keep the shingles from blowing off. So it was one of those, gee, maybe it'll work, let's give it a try. Oops, bad idea, didn't work. So folks, I messed up. This one didn't work. I was hoping that it would. They might build a statue of me in my high school parking lot in my honor if it did, but I guess that statue is going to have to wait for some other change because this wasn't it. While we were doing all of this, we had a massive failure of SIP panel roofs in Juneau, Alaska. All of the moisture ended up at the ridge. We called it the Wolfgang Puck effect because of the mushrooms growing out of the shingles. It all ended up at the ridge, hence the term ridge rot. If I couldn't get it if I couldn't keep it from getting there, maybe I can get it to leave after the fact. So we started experimenting with vapor diffusion vents before we knew that they would work for regular roofs. We said, can we save damaged SIP roofs? And the answer was, yes, we could. So we did all kinds of experiments. We didn't know how big the ridge vents should be originally. We tried all kinds of materials, and it turned out that that's where we learned initially that vapor diffusion at a ridge has a huge drying potential. Now it turns out that the size of this ridge vent in this image is 3 times what it needed to be, but we didn't know until we did the work. So vapor diffusion vents worked. They initially got their start with us trying to use them to save damaged SIP roof panel systems, and they worked. And we have since modified them to be significantly smaller based on the field experimentation and say, look, can we do this with regular insulation, not with SIP panels? So we did lots of work in Orlando and in Houston, as well as in Chicago, to try to figure out what the limits of the technology were. And we found that too close to the edge in Chicago, performance-wise, not ready for prime time, not an issue at all in hot, humid, and hot, dry climates. So here are some of the technologies. Why holes, round circles? Well, we sometimes in high wind areas don't want to affect the the shear, the diaphragm strength of the roof assembly. So you're going to see holes in high wind areas as opposed to slots in low wind areas. Slots or holes, doesn't matter, it's only the surface area. This is the test structure in Houston, standard ridge vent covered with a vapor open in this membrane. In this case, it's a delta membrane from Casella Dorkin, a standard ridge vent on the top of that, and there's our vapor diffusion port that allows the moisture out. This is the test structure, the test house in Orlando. Similar approach, except we've got tile. We used netted cellulose. We've used, this is John's Manville direct spray fiberglass. All of them work. We didn't, so therefore you could create an unvented conditioned attic in climate zones 1, 2, and 3, but the vapor diffusion port at the top with fiberglass or cellulose, as opposed to having to go to low density or high density spray polyurethane foam. We had a test structure that did this for 17 years in Jacksonville. Yeah, this one is 17 years old, and the sheathing is dry as can be. How do we deal with sweating ducts? Well, as the roofs got lighter, as we added radiant barriers, when we started sizing correctly, the cycle time increased, so the ducts in these attics were colder longer, so they sweated longer. So no good deed shall go unpunished. So as we sized the systems better, we ended up finding that the ductwork themselves became a dehumidification system in the roof. So when we had oversized air conditioning systems, the ducts didn't stay cold long enough, so they would sweat, but then the system would turn off and they would re-evaporate. When we became smart and became more energy efficient, there wasn't sufficient time to allow the moisture to evaporate off of those cold ducts, and in the meanwhile we made them colder. So I'm here to tell you that an R38 roof in Florida with a radiant barrier size to ACA manual J, D, and S, and a vented attic with 1 to 300, there's no way of making that work. It can't work, period, from a moisture perspective. So if we bury the ducts, we have to increase the thermal resistance to control that. So we found that maybe we're going to have to go to R15 ducts. R15 ducts don't exist. But if we bury the ducts and we close the vents and have a vapor diffusion port at the ridge, I'm not going to have sweating. This is kind of breathless here for a moment, folks. I can take regular R6, R8 ducts, bury them in hot, humid climates, not install soffit vents, put in a vapor diffusion ridge vent. I'm not going to sweat anything. I'm dramatically improving the performance. I've reduced the air change. I win in all of those areas. Tastes great, less filling. Less filling. Is this legal? No. The code hasn't been changed to allow this, but it will be in the next round. So the code only allows us to move the insulation to the underside of the roof deck with vapor diffusion. But I'm here to tell you that it works even better when it's on the flat, but it's not allowed yet in the prescriptive side of the code. With that, I'm turning it over back to Pam to tell you where you can get all of this information. Pam?
Thanks, Joe. And you covered a lot of information, and hopefully those code changes do take place and go to the next code cycle. As Joe didn't go into a lot of detail of the actual new code provisions, and well, we mentioned that in the course description about what are these new code changes that are going to take place in the 2018. And they will go into the 2018 IRC. And what I've done is taken what Joe's code proposals were that went through the final code hearings, and they did get approved, and so they are being finalized to be published by ICC. And I created a code brief. There's a lot of good resources out there, and a lot of good researchers doing a lot of good work, and all these technologies and innovations. We created a tool, and what could we do to make it easier for builders, homeowners, and manufacturers and so forth to take all the great stuff that Building America has been doing and use it and effectively use it in a simple, easy way. And the screenshot I'm showing you here, and I'll get back to the code changes, is the Solution Center. This came about a couple years ago, and it was capturing all the materials, a lot of the materials, and things that Building America has been doing for many, many years, and putting it in an easy format for people to go grab. And if you haven't been out to the Solution Center, I really highly advise you go out there and play around with it and take a look at it. And when you get familiar with it, you can even log into it. You can save information. You can save it to what you want to keep, like going out in the field. You can put it on a mobile app and take pictures, CAD drawings, and so forth. There's a lot of information here, so I'm going to quickly go through just a couple of things and then get to the resources that Joe's been talking about, because we have developed some that just deal with vapor diffusion ports. So when you go to the Solution Center, right here on the main page, you'll see that there's a lot of stuff going on. There's program checklists for Energy Star, for net zero energy. There's building components. There's the sales tool. There's climate packages, a library, and that mobile app that I talked about. What I'm going to show you today is just two pieces of it, but again, go out and play with this if you haven't. I'm going to go show you some screenshots of guides and the code briefs. What we've developed in the last year, a little over a year, is code briefs on technologies where maybe there was a code barrier or needed more clarification, and something simple and easy where you could look at this technology, and I'll give you what you would need as far as the specifications from the code, the plan review to it, to inspect to it, and any other resources. Really, it's just compiling all this great research, reviewing the technology, and customizing it into a simple format that you could take, and even a builder, so you're both looking at the same thing, and hopefully this will streamline the design and the compliance process to get these technologies out in the field. So the next screen is, if I click on guides from the Solution Center, there's hundreds of guides in the Solution Center, and they're all different things that are happening. There's for new construction, there's for existing homes, and you can siphon through all these and find which one that you're looking for. You can search on the right. There's a search tool on the right where maybe I just want to look at attics. Maybe I just want to look at whole house or thermal enclosures. And what we're talking about today is unvented attics. So if I click on guides and I want to look at unvented attics, then I would go to the next screen. Go ahead and click it, Joe. And I find the unvented attic, and here's one of the guides. So as I mentioned, there's hundreds of guides in the Solution Center, and how these guides are set up is you'll see these tabs that go across the top. And so for an unvented attic, you have scope, and it defines the information for an unvented attic. And then there's a description, there's success, climate, there's information about climate, training materials, if there's some training materials available on this for attics, CAD drawings, compliance, more, and then sales. So those are the tabs. What I'm going to talk about is the compliance tab. And in the compliance tab is some basically it takes unvented attics and it provides you provisions for Energy Star, for the IRC and ICC. It doesn't provide all of them, but it's just touching on the provisions specific to an unvented attic. But what is more happening now is that we've added to this and added them code compliance briefs to go a little bit further. So you'll see this one has a button. Not all of these guides have a code compliance brief, but some of them do. So that's one way to get to these briefs and to get to this code brief that I'm going to talk about is to get through the guides, find the unvented attic, and if there's that code compliance that button, then you'll see that it also has this additional brief. However, also on the left-hand navigation of this tool is code briefs. So you could click on code briefs and see the whole listing of code briefs that are available. And there's quite a few in there. And if you have any suggestions for new code briefs, please send them in to us. I'd be more than happy to see what your suggestions are. If you have issues that are happening with high-performance homes and you think it would make for a good code brief, that'd be great. We'd like to hear from you. So if I click on code briefs and I scroll down, I can find one that's on controlling moisture for unvented attics. So you can click on, go to the next slide. There we go. So when I click on this code brief, all of these briefs are set up kind of formatted the same way. There's an overview piece kind of talking about the technology or what the brief is about. The next section, and I've kind of combined it here, and I know it's really hard to read, so I highly advise you go out there and take a look at this brief. In the presentation, there is a link to it. The next section is plan review, and what I've taken is, what are the provisions that would be applicable to controlling moisture in an unvented attic? There might be some in the ICC, the IRC, and a lot of it will deal with, well, insulating, you know, and so forth, and the vapor diffusion. But with this one in particular, it was taking what Joe had got approved for the 2018 cycle, and I've added it to this code brief, so you see what's coming. Now, what does this mean? So if you're in a location, and there isn't a state or location that has adopted the 2018, but maybe you want to start looking at designing with these vapor diffusion ports and putting these buildings like that Joe just mentioned in areas where he knows they're successful. You could take this brief, and in the code there's always there's a section in there for alternative materials and design. Just because this isn't adopted yet doesn't mean that maybe you could talk to the code official and see if this will still work. There's our provisions for leniency and using alternative materials, and hopefully that you could start working with this design or the way that we're dealing with these roofs now, and this works for you if this is something that you do. So after plan review, and I have the provisions and the new ones from the 2018, there's another section in that code brief on field inspections. And that's just taking kind of a checklist to say, hey, okay, you've gone through your design, it's been reviewed, plan review's gone through their plan review process, the construction documents all passed. Here are some checklist items that you really need to look at for unvented attics that would be specific to this technology that you should be looking at when you go out doing your field inspections. And then lastly on these briefs is a technical validation or additional resources. And this is where it has maybe links to the codes that have been talked about in the brief, additional reports and research. As Joe has a lot of good research on this technology in specific, but some of those papers can get really long. Code officials sometimes don't have time to go through maybe a 60-page research report. So it's putting those references in here that you can go to if you need to go to that additional detail, maybe to go to all the data that Joe is talking about today. And there's other ones in here as well. That's where they would sit, is in that technical validation, the last part of those code briefs. So with that, that's kind of a quick nutshell on some of these code briefs in the Solution Center. I think page down one more. I want to talk about a couple more, maybe not, a couple more resources. So I talked about the Solution Center. There's a lot of information in there. CAD drawings are great. There's hundreds and hundreds of pictures also that there's wrong and right pictures in there. But with that, we also have the Building America website. The Solution Center is an actual tool that's on the Building America website. And the additional other stuff that's out there that Building America has is you can look at the program overall, what's happening with Building America, what are the research teams doing. There are top innovations. There's climate-specific case studies, a lot of good case studies. We have a newsletter. If you're interested and you're not signed up for the Building America newsletter, you can go do so, and I've provided the link there to go subscribe. There's a publications library as well. And then the PDF of this presentation and it is available right now, and the recording will also be available out on Building America, and there's the link for it as well. So, and then on the next to last slide, and then we're going to take questions. You could click one more, maybe not.
And the slideshow.
Okay, well, the last slide was, I need to have the slide where it shows the AIA slide, Joe.
I don't have it.
Okay. Well, we're going to start taking questions. That's fine. I'm going to bring it up. Here we go. Will you show me, can you see my screen?
I'm not sure.
Can you see my screen yet?
No? Andy's still on hold. I can't see anything. So we'll have to just verbalize the talking.
All right. No, I just can't see my screen. If you could put it back on your presentation, Joe, if you could bring it back up.
All right, can you see me?
I can. And if you could, to make this easy, since we have a lot of people on, I got to provide you the AIA link. And I will verbally tell you, maybe Joe could type it in at the same time. It's really easy. And this is for you to go submit your name for AIA learning units and for the certificate of attendance for self-reporting. It is the HTTPS and then the 2 forward slashes, and it's www.energycodes.gov, and then there's a forward slash, and then it's just the words new code options training credit request, and I'll keep saying it because there's a hyphen in between those words. So it's new, and then hyphen code, and then hyphen options, and then hyphen training. This is a long one. I should have made this shorter. And then hyphen credit, and then hyphen request. If you didn't get this, send an email through the registration when you got your confirmation, and that comes to me, and I'll send it out to you. So if you didn't get the link, I'll send it to you. And also, there was another page that was on additional resources. The link to the Solution Center was there. It's a real easy one at basc.energy.gov. And then there was the code compliance brief. But you can get to the code compliance brief because I showed you screenshots of it. And then there was another really good paper that Joe has done on venting vapors. That will be in the presentation that's out there that you can download as well. So that was the last 2 slides. So I'm going to go ahead and start taking questions if Joe could get that in there. And let's start. We have a few minutes. We still have time to do questions. So one of the questions that came in was, if you have an unvented attic and you have a parapet, would you have to insulate that? Or if you have an overhang with an unvented attic, would you insulate the overhang?
Well, you have to decide whether you want to put the overhang into the conditioned space or outside of the conditioned space.
Right.
So you have to first decide where your thermal boundary is going to be. For example, garages that are attached to a house have roofs in them, and we typically include the garage roof and cannot couple it, the garage attic, when we couple it to the house attic. So the thermal boundary is the ceiling of the garage. With porte-cocheres and semi-conditioned spaces to the outside, depending on the size of the overhang or whatever, you may decide to have it part of the roof or part of the attic, conditioned attic, or not part of the conditioned attic. Usually the smaller overhangs are not part of the conditioned space. The larger ones tend to be. So there isn't a hard and fast rule. It depends on how big the overhang is and what is it actually shading, what's going on underneath it. But you can include it or not include it depending on what's going on underneath it and how big it is. Okay.
I'm sharing my screen because I got a few people that said they could see my screen so that they can see that URL. So I'm going to scroll through some of these questions here. What problems do an air-driven rain cause in rigid vents with a permeable insulation is installed against the roof decking? So what problems do an air-driven rain cause in ridge vents with permeable insulation installed against the roof decking?
Well, the whole point of this is to have a water control layer, an air control layer underneath this ridge vent. So this actually solves the problem with typical ridge vents where wind-driven rain can get in. But we're not allowing the wind-driven rain to get in because that vapor diffusion layer is also a water control layer. So wind-driven rain doesn't enter. And candidly, this approach is a better approach for all vented roofs simply because we're still allowing the water vapor out and now the rainwater won't get in. So I believe that there'll be ridge venting systems that are going to become introduced that are basically going to say, look, our roofs, our ridge vents don't leak rainwater, but they do let the vapor out. So this is actually solves that problem that exists with standard roof technology.
Two questions. So do you see that the provisions that are now in the IRC for this new vapor diffusion port, and again, the language for this is out there on that code brief, so you want to go take a look at it. We didn't go into details of it, but it is there. Do you see it coming into the IECC in a future edition of the IECC? And do you also see, Joe, because it's limited to climate zones 1 and 3, it's going to open up to the other climate zones, because you were talked about the future research that's happening and looking at the other climate zones?
Well, it doesn't need to be in the IECC, it just needs to be in the IRC.
Right.
I mean, there's no reason for it to be in the IECC. This isn't an energy saving feature, this is just simply improving the technology. In terms of will it extend into the other climate zones, the answer is yes, but the language will have to be modified because the other climate zones are going to need more control. We're going to need some kind of a vapor throttle and an air throttle on the underside of this. So this is not ready for prime time in cold climates. So we're still doing the work.
Great. Well, one question. Is an unvented attic less efficient than a traditional vented attic with ducts in the conditioned space? Only because the largest surface area, or are other things like radiant increased too?
The answer is a vented attic with an airtight ceiling and the ductwork in the conditioned space outperforms a conditioned attic in all climates. I think I said that in the presentation earlier on, so it's hard to beat a vented attic in any climate if the ceiling is airtight and the ductwork is inside the conditioned space. Let me repeat this one more time because I've been having this discussion for almost 20 years. The reason that I focused on conditioned unvented attics was because I couldn't get people to put the ductwork inside the conditioned space and I couldn't get the ceilings to be airtight. But by gosh, if I could get my ductwork in the conditioned space and my ceiling airtight, the first best destiny for that roof is going to be vented. Now, here are the caveats to that. In high fire zone areas, those vents are a fire hazard. So when you have wildfire issues, we're going to now go to unvented technology because of the damn fires. You're sitting on a sandbar in the middle of the Gulf of Mexico, say Florida, you have these things called hurricanes. There's no way that we can have vented roofs that don't leak. So we're going to go to some kind of hybrid unvented diffusion technology because vented roofs are a real problem from a wind perspective. So if you take away the extreme loads of wildfire and high winds and a sandbar in the Gulf of Mexico, I'm always going to want to go to a vented attic with mechanical systems located inside with an airtight ceiling.
Great. We are at past 11:30, which is the end of this webinar. Joe, is there any final thing that you would like to say before we end? I know we didn't reach all of the questions. There's still a lot of questions in there. If you still have a question, you have our information, or you can email through the same way that you got that confirmation. They do come to me. But we do appreciate that everyone has, excuse me, attended today. We had quite a big audience. Joe, any last things you'd like to say?
This technology is not ready for cold climates yet. So don't do this in Minnesota. Miami, oh yeah. Houston, oh yeah. Dallas, yeah. The Carolinas, yeah. Boston, no. Chicago, no. We're not ready. We probably will be ready the next round, but we're not ready right now. So be careful here. There's some real exciting opportunities, but you're on your own. You're on your own in these cold climates. Now, if you insist on doing it in a cold climate, give me a call and I'll tell you everything we know at this point in time about cold climates. We're not trying to make the technology a secret, but there isn't enough safety factors to have a blanket recommendation such as a code change work in a cold climate. We don't know what the language would be because we don't really know what the limits to the technology are. So be careful in cold climates, but this is ready for hot, humid, and hot, dry climates.
Great. Well, I appreciate that the Department of Energy allowed us to provide this webinar and both of us to speak today, and Joe's time to go over this as his research, and it's great that he could provide this and get a code change in to show this new technology and to make these buildings safer and more energy efficient, right? So thank you everyone for joining us today. Please go out and take a look at the Solution Center and definitely the code brief. It does talk specific on what Joe discussed today. And all of you can hang up and disconnect. Thank you again.